Okay, so here in this lecture, we'll be looking at how glomerular filtration is involved in the processes that lead to production of urine. So we'll be investigating that process in depth, but we'll be looking at all of the processes in, as an overview that are involved in making urine. So here we go. All right, so the material that gets squeezed out of the blood into the glomerular capsule and the material, the urine that we pee, have very different composition. And that is all the result of the work of the nephron tubule. So all of the plasma that gets filtered out of the blood is really different than the urine that we produce. And it's because of the work of the nephron tubule that we see big differences there. So first, here's the overview. There are three processes that are involved in producing urine, and the first is called glomerular filtration. So this is the process that squeezes all of the plasma out of the glomerulus, not all the plasma, but it squeezes plasma from the capillaries of the glomerulus. And in that process, we will make, over the course of a day, somewhere on the order of 180 liters of plasma that gets squeezed out of the glomerulus, out of the blood that comes to the kidney. That's something on the order of 45 gallons every day. And of course, we don't pee out 45 gallons. What we pee out is a much more concentrated material, and that has been enriched with waste products. So we reclaim something on the order of 99% of the water that gets squeezed out of the blood. And so over the course of one day, we filter the blood plasma about 60 times. The second process that's involved in making urine from tubular fluid is what's referred to as tubular reabsorption. So I want to remind you of what we said in the last lecture, that anytime material is placed into the renal tubule, it's on its way to being outside of the body. So if we call something out of that developing urine, out of the glomerular filtrate, and bring it back into the interstitial fluids of the body, that is referred to as tubular reabsorption. And so the renal tubule selectively reabsorbs water. Let's see if I can do this more slowly. Reabsorbs water. We reabsorb electrolytes like sodium, potassium, and other electrolytes, and glucose. All of these are called out of the developing urine and into the blood, or into the body fluids. On the other hand, if we have something that we specifically want to remove from the body, and it doesn't get squeezed out through glomerular filtration, then the renal tubule can selectively place those materials into the developing urine. And so stuff like hydrogen ions, as we're regulating pH of the body, and other toxins and waste materials can all be secreted into the developing urine. So be careful as you are working your way through this chapter. One of the biggest things that people get confused about is which way materials are going in tubular reabsorption and tubular secretion. Reabsorption is about reclaiming materials and bringing them back into body fluids, while tubular secretion is about putting materials into the developing urine. So the total urinary output that we produce is the product, or not product, but the sum of all of the material that gets squeezed out of the glomerulus. So that's the glomerular filtration, plus everything that gets added into it specifically, that's tubular secretion, minus anything that gets reabsorbed back into the body. So let's look a little more closely at glomerular filtration itself. So it's a passive process. It's done by blood pressure. The blood pressure pushes plasma with whatever nutrients are dissolved in it and whatever waste materials are dissolved in it. Pushes it through the gaps, the spaces between the cells of the endothelium that is the capillary. And the fenestrae are there as well, and they are kind of creating this interlaced sieve that helps to maintain any of the proteins and other large materials inside the capillary. And so this process of filtration produces a fluid called glomerular filtrate. And again, it's those fenestrae created by the podocytes that ensure that the plasma proteins remain in the blood. So what gets lost into the glomerular filtrate? Well, water for sure. Waste materials like urea and uric acid, glucose, creatine and creatinine. What are those? Hopefully you remember back to muscles. We require, or creatine helps to, it's a way of helping to fuel muscle contractions because it provides a store of oxygen that allows the muscle to contract, to run cellular respiration in order to make ATP energy. Lots of ions, electrolytes like sodium and potassium, chlorine, potassium. I screwed up again, it looks like. H2CO3 minus, that should really be HCO3 minus. That's the bicarbonate ion. PO4 3 minus, SO4 2 minus. Those are the phosphate and sulfate ions. And other materials are all lost into the glomerular filtrate from the capillaries. So the red blood cells remain in the blood. Most of the plasma proteins, very few get lost in a healthy kidney, and enough water that is drawn back in or maintained in the blood because of all those plasma proteins. So there's a significant amount of things that cannot escape from the blood, and then enough water to keep the blood flowing. So where does the blood pressure, or that filtration pressure, come from? As we said, blood pressure is a big source, the primary source of the hydrostatic pressure that causes filtration to occur there at the glomerulus. So how do we do this? The afferent arteriole, the one coming into the glomerulus, is larger in diameter than the outgoing or efferent arteriole. So just like if we're looking at traffic in a city, if we have a 4-lane highway coming into downtown and only a single-lane highway leaving downtown, what's going to happen? We're going to get a big old traffic jam. It's the same here, but rather than a traffic jam, what happens is blood backs up in the glomerulus and pressure increases even more, forcing even more fluid from the blood. Working against that hydrostatic pressure is colloid osmotic pressure. So all of those proteins that we find in the blood that can be that helps to call fluids back into the capillaries of the glomerulus. So it's working in opposition to filtration pressure. And as well, if fluid builds up in the glomerular capsule itself, then that fluid will have its own pressure. It's going to be working against that filtration. So the overall or net filtration pressure is the result of glomerular pressure minus whatever the colloid osmotic pressure is, minus that capsule hydrostatic pressure that may be there. So what are the relationships between filtration rate and blood pressure and other characteristics? Well, because the primary power behind blood pressure is if that pressure increases, then it's going to push more fluid out. And blood pressure is usually that most important factor in maintaining glomerular filtration rate, because blood pressure is generally higher than the colloid osmotic pressure that's working against the blood pressure to move things out of the body and into the renal tubules. If we decrease colloid osmotic pressure of the blood, that is, if some of those proteins were to leak out of the blood vessel somewhere in the body, if we reduce colloid osmotic pressure, then we're going to see an increase in glomerular filtration rate. And then finally, glomerular filtration rate, as we said before, is heavily dependent on low capsule hydrostatic pressure. So if the hydrostatic pressure of fluid in the capsule increases because, say, there's a blockage in the flow, maybe we get a collecting duct that develops a large stone, kidney stone, then that blockage, as it makes its way through the narrow passageways of the male reproductive system, that blockage would cause fluid to back up in the glomerular capsule, and with that fluid would come pressure. And so if we increase the hydrostatic pressure of the capsule, then we're going to see that glomerular filtration rate is decreased. So we increase it by increasing blood pressure, we increase it by decreasing colloid osmotic pressure of the blood, and we decrease it by increasing hydrostatic pressure there inside of the glomerulus. Okay. So how do we control all of this? So it's great that we got these ways of dealing with it. How do we control it? Well, auto-regulation is one means of controlling. Auto means self. So self-regulation is what auto-regulation is describing. And it maintains filtration rate through sympathetic control. Sorry, all my papers are making a big old noise. So this is the rest and digest system, not the fight or flight one. And also because of reflexive contractions of smooth muscle there in the blood vessels. So if we see a decrease in blood pressure, then what happens is that both the arteriole leading into the glomerulus and the arteriole taking blood away from the glomerulus, they both constrict to help maintain increased blood pressure. Because, of course, if you constrict a blood vessel, then you're going to see blood pressure rise in response. If just the afferent arteriole is constricted, then we're going to see less blood entering the glomerulus, and we're going to see a decrease in filtration pressure. But that constriction of the efferent arteriole will help to counteract the decreased filtration rate that would happen because we're not letting a lot of blood into the glomerulus. So that's why constriction would reduce pressure. So we see this constriction of both the afferent and efferent arteriole if blood pressure is lost. So there are also hormones that are involved in regulating glomerular filtration or a hormone-like materials. So if there's a decrease in blood pressure, the sympathetic nerves and some pressure-sensitive regions of the kidney will secrete an enzyme called renin. So renin is produced as blood pressure is decreased. So as well, if we see a decrease in sodium, potassium, and chloride ions, then the macula densa, remember these are the densely packed cells there in the, shoot, now I've forgotten, macula densa, that is kidney side, if I remember correctly. Let's see. Let me just make sure. I want to make sure that I've gotten that right. Oh, I'm sorry. Yeah, yes, it's where the nephron loop makes contact. That's the macula densa. So that's kidney cells that will secrete that same that will secrete renin. So renin plus a material that's already found in the blood called angiotensin. Together, the enzyme renin will change angiotensin into a structure to a protein called angiotensin 1. So in the lungs, angiotensin 1 is converted into angiotensin 2, and as we make this angiotensin 2, then we see a couple of effects downstream. First, we see vasoconstriction of both afferent and efferent arteriole. As we've indicated, constricting those will help to maintain blood pressure. There's also release of aldosterone from the cortex of the adrenal medulla. And as a result of aldosterone being released, we see sodium reabsorption. So we bring sodium from the developing tubular fluid. That we bring that sodium into the body. So reabsorption again is drawing back those materials that we want to maintain in the body. And then last of all, there is release of antidiuretic hormone. ADH is what it's called. That's the abbreviation for it. And with antidiuretic hormone being released, then we'll see a little bit later why this works, but we see the retention of water in the body. So a diuretic is something that makes you pee a lot and lose water. Antidiuretic hormone works in opposition to that, so that we wind up retaining water when antidiuretic hormone is in the blood. Okay, so first thing, this renin-angiotensin system will help to raise blood pressure once again through sodium reabsorption, which helps to retain water, through antidiuretic hormone, which also helps the body to retain water. And then also a material called atrial natriuretic peptide. So atrial natriuretic peptide, ANP, is secreted by the heart if the heart notices that blood volume increases. And so as a result of that, we'll see the loss of more sodium from the body because we see increases in glomerular filtration rate. And so much sodium gets lost through that process that the blood pressure will then, or blood volume is going to decrease, and blood pressure will also decrease. Okay, so two ways that we regulate glomerular filtration through chemical means: the renin-angiotensin system and the atrial natriuretic peptide system.